Hi everyone, this is Mrs. G.A. and today we're going to learn about geometric sequences and series, but first please pause the video and give this warm-up a try. Alright, go ahead and check your work here. So I've listed out the first 5 terms. For here, for part A, 1, 2, 4, 8, 16. So maybe you notice that you're multiplying by 2 to get to the next term. For the next one, here's the 5 terms. Maybe you notice that the pattern is multiplying by -3. And for the last one, here's the 5 terms. This one, maybe you wrote divided by 2. I wrote multiplied by 1/2, which of course means the same thing. The reason why I wrote it like this is because I noticed another pattern. I noticed that the number you multiply by is the number at the base of our exponential term. Times 2, this is a 2. Times -3, this is a -3. Times 1/2, this is a 1/2. And then another pattern I noticed is that the first term of my sequence is the coefficient of that exponential term. Here, there's a 1 is my first term, and that would be the coefficient. 2 is my first term, we multiply by 2. 32 is my first term, multiply by 32. So this is part of the rule for making what's called a geometric sequence. Again, maybe you already guessed that these are geometric sequences. So remember, last lesson we learned about arithmetic sequences where you added or subtracted by the same number to get to the next term. Today we're going to be doing geometric sequences. So as we just talked about in the warm-up, a geometric sequence is a sequence that has a common ratio between consecutive terms, meaning that you multiply by the same value to get the next term. So here's a couple examples. We saw part of this in the warm-up. Times 2, times 2, times 2, times 2. Times 1/3, times 1/3, times 1/3, times 1/3. Here's some non-examples. So this one, 1, 2, 3, 4, 5. We're just adding a term, so that'd be arithmetic. This one, 1, 4, 9, 16, 25. So these are perfect squares. But again, even though there is a pattern to it, it would not be considered a geometric sequence. All right, now let's look at the rule for writing a geometric sequence, which we did see essentially in the warm-up. So you can describe the nth term of a geometric sequence with the first term and the common ratio. So remember, first term would be a sub 1, and the common ratio, we're calling that r, which is what you're multiplying by to get to the next term. So here's the formula. A sub n equals a sub 1 times r to the power of n minus 1. So you're simply just taking those things, like if your first term was 2 and your common ratio was 3, you're taking those and you're substituting them into the formula. I do want to remind you that here you're going to feel really tempted to multiply the 2 and the 3. However, according to order of operations, we always do exponents before we multiply. So 3 is being raised to the power of n minus 1. 2 is not. So you actually cannot multiply these two terms. Even though it looks like you should be able to do something here, you actually can't. All right, let's give this a try. We're going to write a rule for the nth term of each sequence, and then we're going to find the 8th term using that rule. So for these, since we're given the sequence, we can see what the first term is. I can see that a sub 1 is 5. That's my first term. Now, sometimes when you're looking for the common ratio, the pattern is pretty clear. Like I can see here that I'm multiplying by 3 to get to the next term. But let's say you didn't know how, or you couldn't tell just by looking, or maybe it's a little bit trickier. The way you can always find the common ratio is you can take any term and divide it by the term before it. Because essentially we're doing this term times r should equal this term. So if you take 15 and you divide it by the term before, you get 3. This should work for any term. So if you take the third term, 45, and you divide it by the term before, you should also get 3. Let's check that it's true for all of them. So this is how you can find a common ratio. You can take any term and divide it by the term before, and that should give you the common ratio. And it should be the same as you move to each consecutive term. All right, so I have a sub 1 and I have r. So I'm going to plug it into my formula, which I'm going to write as many times as I can today. So a sub n equals 5 times 3 to the power of n minus 1. So there's my rule. And now I'm going to use that rule to help us find the 8th term. So 5 times 3 to the power of 8 minus 1. So we're going to do 5 times 3 to the power of 7, which is 10,935. So again, we probably could have just continued this pattern by hand and times 3, write it down, times 3, write it down. But if you have a rule, it allows you to find any term in your sequence a little bit faster. All right, let's look at this next one. So again, I can see that my first term is 88. To find the second term, maybe you could tell what it is, but let's do our rule. We'll just do it for one. Take any term and then divide it by the term before. So negative 44 divided by 88 is negative 1/2. So that is my common ratio. And you'll see when your common ratio is negative, you're going to have that alternating pattern between positive, negative, positive, negative. All right, so here's my geometric sequence formula. A sub 1 is 88, and then times negative 1/2 to the power of n minus 1. And then we're going to use that to find the 8th term. All right, so this is going to become, it's going to be negative because I have a negative number to an odd power, negative to the power of 7. And then my numerator is going to be 88, and my denominator is going to be 2 to the power of 7, which is 128. And then, of course, we're always going to try to simplify, so this one becomes negative 11 over 16. There you go. All right, go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work here. So for part A, the first term is 6. Our common ratio is 1/3. So here's my rule. And the 10th term, when you simplify, becomes 2 over 6,561. For part B, my first term is 10. My common ratio is 2. My rule is here, and my 10th term is 5,120. All right, let's give this one a try together. So this says one term of a geometric sequence. It is important that they tell us it's geometric if we don't have more context. Is a sub 4 equals 12. So they're telling us the 4th term is 12. They are also telling us that the common ratio is 2. So we're going to write a rule for the nth term, and then we're going to graph the first 6 terms on this axis. Okay, so we know from our formula that we need a sub 1 and r. So we are given r. We know that r is 2, but we don't know a sub 1. So we're going to have to temporarily substitute 4 and 12 to help us find a sub 1. So I'm going to plug in r equals 2. We want to keep that anyways. And then I'm going to use this piece of information. Again, I'm replacing a sub n with 12. My r value is 2. And I'm temporarily replacing 4, or n, with 4. And you can see that when I do that, my only variable left is a sub 1, which is what I'm trying to find. So we have 12 equals a sub 1 times 2 cubed, which is 8. So a sub 1 is 12 over 8, which is 3 over 2. So now I have all the information I need to actually make my rule. So we have a sub n equals 3 over 2 times 2 to the power of n minus 1. So there's my rule. And here we're going to graph the first 6 terms. So we have some n values, and we'll have the actual term. So we'll do the first 6. So we already know that the first term is 3 over 2. And if you know what the common ratio is, we can just double that term. And there's our next term. We double that. We multiply by 2 again. We multiply by 2, and we multiply by 2. So if we go to plot these points, again, you're going to just need to estimate for them. So 1, 3 halves really close to 0. 2, 3, a little bit above that. 3, 6, maybe somewhere around here. Remember, each of these lines is 10. So we have 4, 12, 5, 24, and 6, 48. There we go. So if you look at the general shape that these terms make when we plot them, you'll see it actually looks like a function we've worked with before. These look like exponential functions. So when something grows by multiplying by the same number each time, that is the definition of exponential growth. So these geometric sequences are essentially just exponential functions, but again, we're not going to connect everything in between because we're only working with whole number n values. But when you plot these points, they should end up looking like an exponential function. And then if your r value is less than 1, you'll see that you have like a decreasing graph, but it would still look like an exponential function. All right, here's one for you to try on your own, so please pause the video. All right, go ahead and check your work here. We were given our r value, our common ratio, but in order to find a sub 1, we need to use this extra piece of information. When n is 5, my term is 2. So I substituted that here and here. I plugged in my common ratio, and that allowed me to find that the first term is 32. So then here's my rule. Here's my first 6 terms, and you can see when I graph them, it still looks like an exponential function, but this time it looks like an exponential decay function. All right, so now we're going to try one of the trickier ones, which is when they don't give us the common ratio or the first term. But here they do tell us that 2 terms of a geometric sequence are a sub 2 equals 12 and a sub 5 equals negative 768. So there's 2 different ways we can do this. So the first way I'm going to show you is creating a system of equations. Okay, for this system, I'm going to temporarily substitute the 2 pieces of information to give me 2 equations, because again, we need to find a sub 1 and r. So if you need to find 2 things, we need 2 equations to do so. So I'm going to temporarily substitute. So I have 12 equals a sub 1 times r to the power of 2 minus 1. And here I have negative 768 equals a sub 1 times r to the power of 5 minus 1. So for this, we're going to use substitution, which means I'm going to isolate for one variable and plug it into the other. So it's usually easiest to isolate a sub 1 here. So first I'm going to simplify this a little bit. R to the 2 minus 1 is just r. So I'm going to isolate a sub 1 by dividing both sides by r. So 12 over r equals a sub 1. So I'm going to take this and I'm going to substitute it into my second equation. So we have negative 768 equals, instead of a sub 1, I'm going to write 12 over r and then times r to the power of 4. 5 minus 1 is 4. So again, I took this and I substituted it right here. Now I'm going to clean up the right side a little bit because I have r to the 4th divided by r, so that gives me 12r cubed. Then I'm going to solve for r. So I'm going to divide both sides by 12, and I get negative 64 equals r cubed. And remember, the way you get rid of a cube is you cube root both sides. So r is going to be the cube root of negative 64, which is negative 4. Remember, it's okay to take the cube root of a negative. The cube root of a negative will just result in a negative. So once you have your r value, we're going to then take that and we're going to substitute it back to the other side right here to help me find a sub 1. So we have 12 divided by negative 4 equals a sub 1. So I see a sub 1 is negative 3. So now I have the two things that we need. I have a sub 1 and I have r. So I'm ready to make my rule. A sub n equals negative 3 times negative 4 to the power of n minus 1. There you go. All right, now we're going to try the same type of problem, but we're going to do a slightly different approach. Instead of setting up a system, there's a different way we can find our r value. So here we're told that the third term is 20 and the sixth term is negative 160. So if I want to find my r value, here's how I can think about it. If I know that the third term is 20, again, this is when n equals 3, and I know that the sixth term is negative 160, and I know that I'm simply going to just multiply by r 3 times to get to this term, because if I want to start at the third term and get to the sixth term, I have to multiply by r and then r and then r. So I can say 20 times r cubed equals negative 160. Again, because if I want to go from the third term to the sixth term, I need to multiply r 3 times to get there. And then this is just an equation that I can solve. So I can divide both sides by 20, and I get r cubed equals negative 8, and then I can take the cube root of both sides, and I get that r is negative 2. Now, once you have the r value, you still have to find a sub 1, but it's a little bit easier because you're only solving for one thing. So I would temporarily substitute either of my points into this equation. I'll use that first term. So we know 20 equals a sub 1 times r, which we know is negative 2, to the power of 3 minus 1. So negative 2 squared is positive 4, so a sub 1 is 5. So now I have both things that I need, and I can make my rule. So a sub n equals 5 times negative 2 to the power of n minus 1. So again, you can either find the missing values r and a sub 1 by creating a system of equations like we did in the last example, or you can kind of use logic to help you find your r value. You have to say, well, how many times do I have to multiply by r to get to the between the two terms? And then once you have your r value, you can use that to help you solve for a sub 1. All right, go ahead and pause the video and give this one a try on your own, and you could use either method. All right, so here I showed out both ways of doing it, so you can kind of pause the video and take a look at whatever method you did. This was setting up the system of equations and then substituting. So I isolated a sub 1, I substituted, I solved for r, and I substituted. Or you can say, okay, to get from the second to the fourth term, I have to multiply by r 2 times. So 12r squared equals 3, and then you can find r in that way, and then you can substitute one of your terms temporarily to help you find a sub 1. Either way, you end up with the same rule. All right, the last thing we're going to talk about today is finding the sum of a finite geometric series. So again, a series is when you just take the terms in your sequence and then you add them up. So there is a formula for this, which is really nice because if you're adding up a large number of terms, it could be really difficult or time-consuming to do this by hand. So the sum of the first n terms of a geometric series with a common ratio, as long as the common ratio is not equal to 1, we can see here. So the sum of the first n terms, we do a sub 1, which is the first term, times 1 minus r to the power of n, which is, again, the number of terms we're adding up, divided by 1 minus r. So I know this formula looks kind of complicated, but it's actually really easy to use, and you need really two things, a sub 1 and r, and that allows you to add up the first n terms. All right, let's try this one together. So here I can look at the rule that's in my summation notation, and I can see that this is a geometric sequence because it's 4 times 3 to the k minus 1, so it's that same format we've been using. So I know that I'm going to use my geometric series formula, and I'm going to write the formula again as many times as I can to help me memorize it. So I can use my rule right here to help us find a sub 1 and r. So to find a sub 1, we would simply replace k with 1. So let's do that here. A sub 1 equals 4 times 3 to the power of 1 minus 1. We know 3 to the power of 0 is 1, so a sub 1 is 4, which we also know should be this number in front. We do just need to be careful. This is always going to be a sub 1 as long as this says k minus 1. Occasionally you'll see a sequence rule where it just says k. But if you go through the process and you just plug in 1, you should be able to find the first term easily. And then we know that the base of our exponential term is our common ratio. So our common ratio should be 3. But you could always list out a few terms in the sequence and then look for a pattern to find your r value. So we have the two things we need. We have a sub 1 and we have r. And then I can see from my summation notation that I'm finding the sum of the first through 10th term. So the sum of the first 10 terms. So n is 10. And those are the three things I'm going to plug in. So the sum of the first 10 terms is 4 times 1 minus 3 to the power of 10 over 1 minus 3. Here we can use our calculator to help us out. So here we have 4 times, if you do 1 minus 3 to the power of 10, you get negative 59,048, and then divide it by negative 2. And then you're going to multiply that result by 4. And so we get that the sum of the first 10 terms is 118,096. There you go. So you can see that knowing this formula is definitely better than listing out those first 10 terms and then adding them up manually. This is going to save you a lot of time. All right, here's the last you try of the video, so pause the video and give it a shot. All right, go ahead and check your work here. So my first term, I plugged in I equals 1. My first term is 1. My common ratio is 5. The number of terms is 8. And I plugged in those values, and here's my sum. All right, that is all for today's video. Thank you so much for watching.